Yeah, now we come to our today's speakers with the title OPC UA for Powertrain. I would like to welcome Mr. Tobias Hitzel. He is a consultant of VDMA Power Transmission Engineering, and Dr. Oliver Barth. He is head of development of electronics and software from Wittenstein. And now I would like to hand over to you, Tobias.
Yes, thank you very much, Mark, for your introductory words. We want to show you today the information about the activities in the field of powertrain for OPC UA, and therefore we will give you some information to the domain power transmission engineering as information. Then we will go through the use cases, the reason why we started the standardization for sure, and we will take a look at the information model of the powertrain specification. And afterwards, Dr. Oliver Barth will give you some practical implementation examples, how our specification can be used. Yeah, maybe in general, the power transmission engineering is the largest supplier sector of the mechanical and plant engineering industry, with a high diversity of drive system, with a high number of interfaces. It's often a part of more comprehensive system and has a wide range of application where it's used. And for sure, we are on the one hand the producer of data, but on the other hand also the user of the data. And for this, we have a quite central role in the mechanical and plant engineering industry. The main drive technology components and products can be divided in these areas, which you can see here. So it's more the drive elements, the couplings, the bearings, the belts, chain drives, shafts, and brakes. Then we have these area of the gearboxes with gears and variable speed drives. For sure, we have the electrical drive technology with the motors, the gear motors, the drive technologies, the encoder and power electronics. And also we have this area linear technology, which is more the area of mechatronic system and linear techniques. Alone in the VDMA, in our Drive Technology Association, we're representing over 200 member companies. This means we are covering approximately 85% of the German power transmission market. Members from our association employs over 90,000 employees in the sector. We have turnover of 80.2 billion euros. The exports are 70.3 billion euros and the imports 10.2 billion euros, and that's only the mechanical part, because in the VDMA we have only these statistics and information about the mechanical drive technology components, and so the electrical drive components should be on top. And worldwide, the power transmission engineering from Germany has an export rate of 20%, and at the moment, forecast for the nominal sales for 2024 are minus 4%. The working group in our area on OPC UA activities was launched in 2018. So quite a while ago. Thereby internationalization was aimed from the very start, and so the joint working group was formed with the OPC Foundation as a joint working group. And here you can see the companies which have worked and supported our activities since then. And you can see that's all well-known and international active companies, which was also important to strengthen the acceptance of the OPC UA companion spec for the powertrain. Let's take a look to the reason why we started the standardization and also the use cases we addressed. So maybe in general, why we have decided to become active in the field of OPC UA. So Industry 4.0 is overall, in the overall context, offers the potential to establish new opportunities in terms of process optimization, new business models through the digitalization and the network of products and productions, and hierarchical communication dissolved within Industry 4.0 processes in favor of seamless networks. And the basis for mapping this is the availability of interoperable communication interfaces. And this is a possibility OPC UA has offered with standardized architecture and language for machine and components. And this was one point why we started these activities with OPC UA. And in addition, as I said it before, various machine industries approached us here and asked us that the drive technology should deal with OPC UA because we are a central component of the most machines and systems. Yeah, the motivation of starting the activities of OPC UA was basically based on the discussions, challenges, and wishes we received from the user industries. So our aim is to reduce the engineering effort by using cross-manufacturer interoperable information models. We want to add additional standardized services for OEMs and plant operators. We want to ensure a seamless integration of our companion spec for the powertrain in other industry-specific OPC UA companion specifications. And we want to focus on user-centric use cases for vertical communication in the production. And yeah, we quickly realized that the drive technology is such a central field that a high degree of networking is necessary to involve all the stakeholders. And for this reason, we reached out for other groups and got in contact. And for this, we have a close network with the FX Motion Working Group within the OPC UA field level initiative, but also with other working groups here in the VDMA and also with standardization groups like IEC groups. This slide is just to illustrate that we want to cover all types of powertrains, from the simplest form of a powertrain with a motor starter and a motor to a more complex system with motion control or multi-ax systems. We really want to cover all these possibilities, and that we did with our companion specification. Yeah, here you can see the system boundary we gave us for our work on the companion specification. So we are focused on the main elements of a drive system. So we have the drive component related assets, which is a power converter or frequency converter. Then we have the alternatives, the switchgear related assets, the contactors, the soft starters, the motor starter, and the electronic overload relays. And then we have this field of actuator related assets like an encoder, the brake, the motor. And the motor, we have different parts in our specification. We have linear motors, we have rotary motors, drive integrated motors. So we try to cover everything which is possible to combine. And also the gear part. What we didn't want to address is the mains area and also the load side we don't describe in our specification. So this is a complete system what we are covering with our specification. Yeah, in this way we worked on it. Regarding the use cases which we collected for us, so the information model of the powertrain addresses user-related use cases based on vertical communication from the field level up to the cloud. So here we talked a lot with user industries of drive technology. What are the main topics? Important is to say that we have split our companion specification in several parts because we collected so many use cases that we were not able to put everything in one companion specification and wanted to work on the basis in the first step. And for that, the part one of the companion specification for the powertrain provides cross-manufacturer information that enables asset management applications for the user. So that means that the companion specification provides static data of the components and the asset of a powertrain, like the part number, the brand name, serial number, and many things more, which can be found on the catalog data of the components. And as you can see here, the use cases are relevant for the plant processes, but also for a machine in the different stages. So you can have an asset identification to search for a component in the event of fault, even it's difficult to access or the device is on another location. This was one use case we received. The device health is also included and is inherited from the OPC UA specification 10,000-5 unified architecture. So that we also included, and then it's possible to do such sub-use cases, but also do other use cases in the asset management area, which you can see here, and furthermore. Yeah, so this was the information to the use cases and the reason why we did the standardization work. Now we take a look at the base information model of our specification. And here, as I said before, it's important to say, so the part one, the asset model for the use case asset management is completed from the content side. We are at the moment working on the last points for the machine readable node set, but this will be, I guess, released during the summer. So the specification will be available shortly. And then we will go on with the second part of our specification for the powertrain. Yeah, and here you can see the base structure of our asset structure and information model for the powertrain specification. So due to the complexity of the real-world powertrains, the information model must be highly modular, and in this way we defined asset types. These are the types which are related to the orderable parts of a powertrain, so like a motor or gear or drive or a sensor. And these asset types are used as container to collect then the relevant asset attributes, the catalog data, the typical data, the static which is available for that product. And so here we have two different asset attribute types, which are these types for the parameters of the asset types. So we have the asset attributes type, which are mostly directly related to an asset type, like a motor asset type has then also the motor asset attribute type. But there are also some attributes which are common and can be related to different assets, and these are the common asset attribute types. So these types, like standard asset attribute type or communication interface or cooling attributes type, these are common attribute types and can be used in different assets. So this is the base structure. I guess it's quite simple, but there was a lot of work to do because we had so many products which we had to cover here. Yeah, here you can see in this slide the base asset type which we defined, which is a basic type for all assets in the powertrain. And the general assumption here is that any VDMA companion specification shall be in line with the OPC UA for machinery. And as you can see here in the picture, we did that and used already defined things in the OPC UA for machinery part. But we want also to make sure that we are compliant with other specifications like the FX motion specification, and that it's possible that although these working group in the FX motion can use our PT asset type, and therefore we also compliant with the OPC UA 10081, the information model and connecting device specification, and also we are compliant with the drive integration specification here. And here we want to make sure that we are seamlessly integrated also with other specification, and that it's possible to use our specification also in other industries. Yeah, for example, just to show how this is working. So here is the example of the PT asset software starter type. So the software starter type is a subtype of the PT asset type, and there with this the PT asset software starter type inherited some basic properties of the PT asset type, which is a mandatory property, the identification, which you can see below. And then there are optional properties which can be inherited if it's necessary or if this must be used, which is optional from the base PT asset type. And then for sure the PT software starter type has mandatory PT software starter attributes type, which is a subtype of the PT attributes type. And also maybe this PT software starter type has optional properties which can also be used, like the PT communication interface attributes type. And in this way, it's possible to define the different application solutions which are existing in the powertrain, and also different powertrains can be modeled like this. What we also did is that we integrated references to data standards like the IEC Common Data Dictionary. So for that, we made some additional references for our properties. And we worked here together with the IEC standardization group for the switchgear related components. And in this way, it was possible to reference directly our properties to the IEC CDD database. And with that, I would say I'm finished with a basic overview to our information model, and would hand over to Dr. Oliver Barth, who will show some ideas and practical implementation examples how our specification can be used.
Yeah, thank you very much, Tobias. So you heard about the motivations and the theory and the node set we built and we specified. And of course, the main question is, how can I use all this in a practical world? And first, we give you some ideas how to use it, and also we have some examples of the members of our working group, how they do use the work results. So if we are going to the next slide. So question was, what is a good example where we can show the usage of the companion specification? And I think what you all might know is the nameplate. So it's a typical nameplate you find on each and every motor, for example. And it holds the typical data you need to look up and characterizes the motor. So as you know it, the motor type is shown. You see product code, serial number, duty type. And also it may hold the working values, the rated values of some operating points, which are typically expressed in the voltage, in the winding type. So you see the Y winding or the D winding. And you see the frequency and the power, the rated power. And all this shall be accessible by our node set. So the question is, how do you transfer this into an actual node set? A node set which may exist on the controller of the motor or on the overall controller. So this is not strictly defined. The data model can be on any device which holds, which controls the motor, or may even be an edge gateway. And now you see we instantiated our model. So the main object is my motor. Of course, you would use another name for it, but this is just an example, of course. And this the motor we made an object of first has an identification. So this holds product code, serial number, and so on. And the next component you see is that the motor has attributes. So what type of motor is it? You see it's an ASM, an asynchronous machine, and pole pair number is 2. So this part of the nameplate is already translated to the information model. So it has the properties, motor type and motor pole pairs. And now you transfer the table into the model. And for this, you use the motor rotary rated attributes, which we already defined, of course, in the object type definitions. And because you have 3 rows, you need, of course, also 3 objects, which each hold the data of each row. So you have the input interface attributes, which are the rated voltage, the input frequency, input current, and all this is now defined with real-world numbers. So you see the 400 volts working voltage, and you see the input frequency. What's not shown on the picture is that you can, or you also add units. So, of course, the voltage has the units volt, and the frequency is hertz, and the currents may be amperes or kiloamperes. So you can also choose units for these values. Yeah, and you go on and you see motor windings type is a property that we added to the node set, and the motor speed rated, so rated speed of the motor. So left you see the well-known nameplate, right you see the implementation of the values into an object, or let's say the transfer of the values into an object you instantiated using the object definition, the node set of our model. Maybe the question is, when do you fill in these values? Well, of course, in the lifetime of the powertrain asset, or in this case, the motor must be produced. Of course, you must know the values, and it most probably will be added at commissioning, at end of line test and commissioning. And of course, it must be added to the respective controller. Another possibility is if you set up the plant, so before you go into operation, you need add all these values here. Okay, Tobias, thank you. Next slide, please. Good. Now, the companion specifications are not synchronized in time. Some come early, some come later. And of course, it's also possible that you already have decided to develop an OPC UA model for your own, because you see the advantages of interoperability, and this model exists now. And you may have a powertrain part device whatsoever already. So how can you handle the problem, or no, so it's not a problem, but now we release our specification of the powertrain. Is there any possibility to not throw away your existing work? And the good news is yes, there's a possibility. Everything that you already developed can be used, and the workflow is as follows. You have to create, you have to derive from your existing object type. I hope you can read it. So you have an existing asset type in green in the gray box, and you derive a new enhanced motor asset type. And this motor type shall use parts of our specification. You can completely decide which parts you think are useful, and then you enrich your derived model. And the workflow is as follows. There are two types of references we recommend to use. The one has interface, and as you see in the drawing, you can freely decide. So let's say you want the iMachinery vendor nameplate interface from the machinery specification. You can just include it by adding a reference. Or you say you want the device health type from the device integration companion specification. You can also integrate by using the has interface reference. So this is a very elegant and easy way to enrich your own object type. Of course, you can also add components like the identification or like the motor, or like any other of our motor attributes, and there you're using the has add-in reference. And then you can just pick the attributes or assets of your choice and include it into your own implementation. Later, if you instantiate your object type into an object, you see it on the bottom part of the picture. It's called motor 1. So this is a real motor. You instantiate it, you build the motor and you instantiate the model, and then you can make use of all the items that you included, that you use to enrich your model. So this is a possibility. And of course, it makes it easier to use our work results. It's not necessary to throw away existing work. And this is a very elegant way to participate in our work. Yeah, there's some special ideas behind it that may go too deep now. So we already created default browse names, and if you include just an attribute of our specification, you will see the reference to the specification by the default browse name. And also, if you include an attribute from our specification, there's a special reference which is called has Powertrain attribute. So this is some more convenience to use our specification in maybe existing work. Thank you very much, Tobias. Good. Now maybe the most interesting part, how do you use it in real products? And of course, our working group which is on the subject now, let's say for 5 years, has a purpose to put it into our product. Of course, I mean, this is a lot of work and we want to have a benefit from it. And here you see some examples how we will use our companion specifications. The first one is from company Wittgenstein, where I am from. So we have a small servo drive portfolio. It consists of servo motors and inverters. And here on the inverter side, we have the possibility to integrate the specification. So we have a special ASIC, which is just for communication. So that's why we have all the interfaces like EtherCAT and Profinet and Ethernet IP and so on. And this also allows us to implement an OPC UA server. And this is done at the moment. So for us as a component supplier, it is mandatory to be connective. So we don't sell controllers, and our success is dependent on our connectivity. And an OPC UA is excellent addition to the existing real-time field buses. And of course, what we have provided now in the working group is asset management, but we will add some more use cases, which we'll introduce in the next slides. So this was an example from Wittgenstein, and the next slide shows an example from Siemens. And also, it's, I think, noteworthy that Siemens equips all the drives now with an OPC UA server. So this is standard now for Siemens. Also for them, the asset management was one of the main drivers to do it. And as you've seen, the asset management was one of the first topics we implemented here. But as the slide is created by Siemens, they also show the other intentions. And as you can see, it's in the field of condition monitoring and quality management and so on. And again, in parallel to the real-time field bus, they provide an own OPC UA standardized interface in all their drives. So that's interesting, I think. Thank you, Tobias. Yeah, another example which is not a drive. I think that's also nice to see that, as Tobias said, the powertrain consists of a lot of components which can be combined in a lot of ways. And here you have an example from an encoder. The encoder holds indeed an OPC UA server, and if you look at the slides or read the description, it delivers all the field bus real-time data in a usual way with the typical real-time field buses, but it has an additional OPC UA channel which serves for the purposes which we already been talking about. So it's like commissioning, asset management, and so on. And I think what's interesting is that you have a not so big device like an encoder, but it has enough computational power to provide an OPC UA server. So there's of course some effort necessary. You of course need a controller and a RAM, an additional RAM, and so on. But they put all this highly integrated into an encoder device, and also provide it as an additional interface. So another connector is of course necessary to connect to TCP/IP, and I think it's a nice example that the value of an OPC UA server is seen very, very high, because space is valuable in this kind of devices, but still they implemented the OPC UA server. Okay, going to the next slide, we see the company Flender. And yeah, the first question of us was, what means AIQ? So AIQ products, it's a combination of artificial intelligence and intelligence quotient, or intelligence, yeah. And in this, in the gearboxes is now sensor device, which can monitor, I think, we see speed, torque, vibration, temperature, so and coupling wear, and yeah, it's a typical Industry 4.0 use case where you try to provide additional information, for example, for condition monitoring and lifetime and predictive maintenance. And also for Flender here, it was clear they wanted to choose the OPC UA because it's simply interoperable field bus technology and becoming really the standard for the Industry 4.0 topics. Good, I think the next slide, Tobias, is from Lense. Yeah, from Lense you see also another aspect. As I said, the question is, where do you implement the OPC UA server? And Lense in this example is implementing it in the controller. and alternatively implementing in an edge device. And they have special terminology and also made some software to use it easily. So I'm not completely in detail with these slides. It's just an overview, but I think you can map data between OPC UA and real-time data you acquire and so on. And as you see, there are many possibilities for the location to implement the server. Let's come from top to down. It's the edge gateway, it's the controller. And as you can see, they also plan to implement it on the drive itself. So this is also a possibility. Thank you, Tobias. Yeah, I think last but not least, ABB. Here is also it's also a very active member of our joint working group community, and also for ABB it was clear that the results will be put into the devices as soon as they are available. They also provide an OPC UA server for condition monitoring and analytics, and it's just mentioned, as you already know, we have the asset management as our first use case. And ABB already did a little more or some more. So they have also events which are part of the OPC UA specification. You can be notified if some limit values may be reached or so on. So this is all. Also, this is a parallel implementation to the real-time field bus. Thank you. Okay. Now you may wonder what the next steps are. So the asset management is finished, and at the moment the node set is tested in prototypes by the members of the working group. But of course it shall not be the end of our work, and the next steps are listed on this slide here. The next use cases are, of course, we want to transmit functional operation data that typically are like currents and velocities and speeds and so on. And we want to add diagnosis. So we have a very little diagnosis already with health value and so on. But of course, Industry 4.0 is, let's say, has a strong focus on diagnose. Diagnose may also mean you have kind of oscilloscope functionality, but it can be everything like logging data in general, or limit values or alarms or whatsoever. And of course, condition monitoring is then the topic we will also address in the next steps. You see the join the team. So I don't know if you mentioned it already, but the working group is open, and we are very happy about anybody who wants to join. I think we have a very efficient team now. It took some time to get to know the OPC UA specifics and to learn how to write a specification, but we can do this now, and we will go on efficiently. And as Powertrain has really a lot of possible components, we are happy about any support which joins us.